Asterisk, your brain can command a robot even when your body is still. Asterisk, how does that happen? An adaptive neural interface learns from your thoughts in real time, decoding the electrical language of neurons and tweaking its algorithms as you practice. It turns silent intent into motion. Watch how it works. Neurons send brief electrical bursts called spikes that travel along axons. Tiny electrodes on the cortex capture these spikes and feed them into a computer. The system filters noise and amplifies the signals in real time. A machine learning decoder then matches spike patterns to specific intentions, like moving a cursor or turning a wheel. Because each brain is unique, the decoder learns the individual code during calibration sessions and keeps updating as signal quality changes. Neurons send brief electrical bursts called spikes that travel along axons. Tiny electrodes on the cortex capture these spikes and feed them into a computer. The system filters noise and amplifies the signals in real time. A machine learning decoder then matches spike patterns to specific intentions, like moving a cursor or turning a wheel. Because each brain is unique, the decoder learns the individual code during calibration sessions and keeps updating as signal quality changes movement. The adaptive element ensures that even if electrode contact shifts, the system still interprets the signals correctly. This closed-loop design turns thoughts into action with minimal effort from the patient. In practice, patients experience a sense of agency that was previously impossible. Pause 0.8. Neurons communicate by generating brief electrical spikes called action potentials. Each spike travels along a neuron's axon to the next cell in the circuit. The timing of these spikes encodes information about intended movements. When many neurons fire together, their combined pattern forms a distinct code. Brain-computer interfaces capture this activity with electrodes placed on the cortex. By decoding spike patterns, the system translates intent into commands for external devices. Thus, even when muscles cannot move, the brain's electrical language remains accessible. Pause 0.8. First, we look at the skull in 3D. On one side sits a tiny microelectrode array. It is implanted directly into motor cortex tissue. The other side shows a flexible surface electrode. This sits on the skin above the same region. Implanted arrays record signals with high spatial resolution. Surface electrodes capture broader, noisier activity from many neurons. Signal quality is measured by signal-to-noise ratio. Higher ratios mean clearer commands for the interface. Thus, placement determines how well a patient can control devices. Pause 0.8. Neural spikes are brief electrical bursts that travel along motor neurons. The first step is to detect these spikes in the recorded signal. Once detected, we extract features such as spike amplitude and timing. These numerical features become inputs for a machine learning classifier. During training, the system learns which feature patterns correspond to specific hand movements. The classifier then assigns each new pattern a discrete command label. A command like move left is translated into a signal for an external device. Thus, raw neural activity becomes actionable instructions in real time. This decoding pipeline allows paralyzed patients to control prosthetic limbs or cursors. The flowchart visualizes each stage from spike detection to command output. Pause 0.8. The system monitors the patient's brain signals in real time. It compares the predicted movement to the actual intended action. When a mismatch occurs, an error flag is raised automatically. This flag triggers a brief reinforcement signal sent back to the interface. The interface uses this signal to adjust its decoding parameters slightly. Over successive trials, these adjustments reduce future errors steadily. A line graph shows the error rate dropping across sessions. Each highlighted point on the graph represents a successful correction event. As accuracy improves, the patient can command external devices more reliably. The loop continues until performance reaches a stable high level. Pause 0.8. The brain sends electrical patterns that the system captures. Sensors translate spikes into digital signals for analysis. A decoding algorithm maps these patterns to intended movements. Processing occurs in milliseconds, ensuring minimal delay. Decoded commands are sent to a robotic arm controller. The arm follows the patient's imagined motion precisely. Similarly, a powered wheelchair receives steering instructions. Both devices respond within 1 second of thought. This real-time loop closes the brain-to-device gap. Patients can now navigate environments with newfound freedom. Pause 0.8's clinical trials show that adaptive neural interfaces can restore basic hand movements in about 70% of participants. Success rates vary with electrode type. Flexible polymer arrays tend to maintain signal quality longer than rigid silicon probes. Decoding accuracy improves after a few weeks of calibration, but initial performance often drops during the first day of use. Signal stability is limited by tissue response and micromotion, leading to drift that requires periodic recalibration. User training remains essential. Patients must learn to modulate neural activity consciously for reliable control. Closed-loop feedback providing sensory cues back to the brain has begun to reduce error rates in real-time tasks. Long-term safety studies are still sparse, with few participants monitored beyond 2 years post-implantation. Open research questions include how to automate calibration and to integrate multimodal signals like EMG or eye tracking. Future directions point toward fully implantable systems that combine power harvesting, wireless data transfer, and adaptive decoding algorithms. Ultimately, the goal is a seamless interface where neural intent directly drives external devices without conscious effort. Pause 0.8's adaptive neural interfaces convert the brain's electrical language into real-time control of external devices, learning from user feedback to improve precision. This technology offers paralyzed patients a new pathway for interaction and holds promise for future neuroprosthetic advances.